All right, this is our walkthrough for the homework assignment titled Limits 4. So we're going to start off with some trig limits. So what we need to remember is that we proved in class that the limit as u approaches 0 of the sine of u over u is equal to 1, right? Where u can be any function as long as when whatever we've got here is approaching 0, whatever variable is approaching 0, that function is still approaching 0. So that's what we're going to do here with this limit. The limit is theta approaches 0 of sine to the fourth 3 theta over 2 theta to the fourth. So another rule we had was constants can be pulled out of limits. So generally that's going to be our first step. So we'll take that 2 that's in the denominator out into the front and just write this as the limit, or 1/2 of the limit, as theta approaches 0 of the sine of 3 theta to the fourth, right? Because that's what the sine to the fourth of 3 theta looks like. That's the same thing, over theta to the fourth. And then this makes it pretty obvious that both the numerator and the denominator are being raised to the fourth power. So we could then rewrite this as a limit as theta approaches 0 of the sine of 3 theta over theta, all being raised to the fourth power. And so now, what we're hoping to do is get something of this form inside of our limit. So we have the sine of 3 theta over theta. Well, we'd like the sine of u over u. So we'd like the sine of 3 theta over 3 theta. We can't just put a 3 in there without putting a 3 in the numerator as well. Now we, again, don't have this limit because we have a constant up here in front of that sign. So what we want to do is we want to pull that constant out. And as we do that, as we pull that constant out, we need to remember that that constant is being raised to the power of 4. So this now becomes 3 to the fourth power over 2 times the limit as theta approaches 0 of the sine of 3 theta over 3 theta to the fourth power, which now looks almost like this. We just have a fourth power around it. Well, another rule that we talked about for limits was that if the thing inside the limit is being raised to a power, you can pull that power outside the entire limit. So now we can do the 3 to the fourth, which is 81. So we have 81 halves. And then we can just pull that power all the way outside the limit. So we have the limit as theta approaches 0 of sine 3 theta over 3 theta, all being raised to the power of 4. And while our u here, 3 theta, is not the same as this, we again talked about in class that as long as theta approaches 0, this 3 theta over 3 theta, as long as those are the same, and they're both approaching 0, right, which they are when theta approaches 0, then this still equals 1. So we can now say this is the same as 81 halves times 1 to the fourth power, which is, of course, just 81 halves. And so as we do the rest of these, we're kind of going to skip a couple little steps along the way, hopefully. We'll still do all the work and talk about what's going on, but we should be able to skip a little bit of the steps for some of them. All right, so for this one, it doesn't quite look the same. So what we want to try and do, we should have done this for the first one too, is just note that it's 0 over 0. And this is also 0 over 0. Right? This is 3 minus 3 times the cosine squared of 0, which is not theta, 0, all divided by 5 times 0, right, which is 3 minus 3, or 0 over 0. So what we'll do is we'll simplify. We'll write that this is the same as the limit as x approaches 0 of 3 times 1 minus cosine squared x, right, all over 5x. And so if we look at that, well, we should recognize then that we can turn that 1 minus cosine squared x into a sine squared x. And we can also take both the 3 and the 5 in the numerator and the denominator and pull them out into the front. So we end up with 3/5 of the limit as x approaches 0 of sine squared x over x. Right? And so the reason we want to do that is because we know how to deal with the limit as x approaches 0 of sine x over x, which is not what we've got, but that's okay, because we can always separate limits out using multiplication, right? Sine squared x is just sine x times sine x. So this can be the limit as x approaches 0 of sine x times the limit as x approaches 0 of sine x over x, right? Because sine x times sine x in the numerators is sine squared x, and a 1 down here times x is just x, right? So this is equivalent to sine squared x over x. So now we'll just evaluate each of these limits. We still have the 3/5 out in front. The limit as x approaches 0 of sine x is just the sine of 0, which is 0. And then the limit as x approaches 0 of sine x is 1, because we know that. And 3/5 times 0 times 1 is just 0. All right, for our next one here, we got a little technique that we'll do here, which is after we recognize that it's 0 over 0, right? It's just the sine of 0 over the sine of 0, which is 0 over 0. We're going to, again, separate this, not into two limits yet, but we will soon. We're going to separate this into the sine of 3x over 1 times 1 over the sine of 7x. Because we don't have a rule dealing with sine of something over the sine of something. But we do have rules for sine x over x or x over sine x. So it'd be nice if this sine of 3x had a 3x in its denominator. So I'm just going to put that 3x there. And in a second, I'll deal with canceling that out in the numerator. But before I do that, we want to look over to the second one, right, which is 1 over the sine of 7x. And another rule we proved, right, that I'll write over here, is that the limit as x approaches 0 of x over sine x is also equal to 1, or u over sine u, as u approaches 0. So it'd be nice if this 1 was actually a 7x. So I'm going to put that up there, and we'll deal with canceling it out in the denominator in a second. But before we do that, we'll note that, or as we do that, actually, we'll note that we've already put an x in the denominator and an x in the numerator. So those are good. We don't need to add an x up here and an x down here, because we've already multiplied both the top and the bottom of this by x. So the x's are good. We just need to put a 7 in the denominator and a 3 in the numerator, which conveniently can just both be thrown out into the front of this limit. So we'll just call this 3/7. And now I have a limit as x approaches 0 of sine 3x over 3x times 7x over sine 7x. Well, each of those can be written as their own separate limits, just being multiplied together. And now we have 3/7 times the limit as x approaches 0 of sine 3x over 3x, which is just 1, times the limit as x approaches 0 of 7x over sine 7x, which is also just 1. So we end up with 3/7 times 1, or just 3/7. All right, for number 4 here, for our next one, we're going to have to start getting a little bit more creative with these. So we've got a theta squared minus a 1 plus cosine theta all over sine squared theta. So the first thing we'd probably note is that theta squared over sine squared theta is very much like theta over sine theta. It's just all being squared. So it might be nice to separate this into two different limits. One that's theta squared over sine squared, and the other one that is the rest of it, right? So we're going to do this as one limit, and we're going to do this as one limit. Right? And so we can do that because we're just adding those two together, and we can always separate limits using addition. So I have the limit as theta approaches 0 of theta squared over sine squared theta. And then we have, we're going to have a limit as theta approaches 0 of a negative 1 plus cosine theta over sine squared theta. Well, this is where your pre-calculus trig stuff is really useful, right? Because we should know that sine squared theta is the same as 1 minus cosine squared theta. And oftentimes in your pre-calc class, you would have converted sine squared into 1 minus cosine squared so that you could then factor 1 minus cosine squared using a difference of squares, right? Which would be 1 minus cosine theta and 1 plus cosine theta. And so we have a negative 1 plus cosine theta in the numerator, which is very much like 1 minus cosine theta, right? Negative 1 plus cosine theta is the same as negative 1 times 1 minus cosine theta. So as I do this, instead of separating these using addition, what I'm going to do is I'm going to put a minus in front, and I'm going to factor out that minus sign from the negative 1 plus cosine theta, which will give me a 1 minus cosine theta over that sine squared theta. And the whole reason we did that is so that we can see that sine squared theta is the same as 1 minus cosine squared theta, which is the same as 1 minus cosine theta times 1 plus cosine theta. So as we go through here, and now we'll write this one as a limit as theta approaches 0 of theta over sine theta all being squared, right? Because if everything inside the limit is being squared, that squared can get pulled out. And then we'll rewrite this one as a limit as theta approaches 0 of 1 minus cosine theta, and then using that logic we just talked about, that sine squared is 1 minus cosine squared, which is 1 minus cosine times 1 plus cosine, we'll put a 1 minus cosine and a 1 plus cosine theta down here. And then we'll cancel out those 1 minus cosine thetas. This one can be evaluated. This is just 1 squared now, minus a limit as theta approaches 0 of 1 over 1 plus cosine theta. Well, 1 squared is 1. And we'll subtract from that 1 over 1 plus the cosine of 0. Well, the cosine of 0 is, I wrote theta, but the cosine of 0 there is 1. And so let's change that. 1 minus the cosine of 0. So this is 1 minus 1 over 1 plus 1, or 1 minus a half, which is just 1 half. All right, for our next one here, we can see that everything inside of this is being cubed. And this time it's tangents instead of sine, but we proved in class that the limit as u approaches 0 of the tangent of u over u is also equal to 1, right? It was pretty easy. We just took tangent, broke it down into sine over cosine, and used the sine rule that we already knew. So we'll see that everything's being raised to the third power. So we have a limit as t approaches 0 of the tangent of 3t over t all being cubed. And so if we could get that denominator to also be 3t, just like the argument of the tangent is, which we can by putting a 3 in the denominator and a 3 in the numerator, then we should be able to turn that limit into 1. But we do have to pull this constant of 3 out, remembering that as we do that, it's not just 3, it's 3 to the power of 3. So we have 3 cubed, now times, since everything in there is now being cubed, we'll pull that cubed outside the entire limit. So it's a limit as t approaches 0 of tangent 3t over 3t all being cubed. So 3 cubed is 27. So we end up with 27 times 1 cubed, which is, of course, just 27. For number 6 here, we want to sort of get creative with our trig and with factoring. So with any luck, we would recognize that 1 minus 2 cosine x plus cosine squared x looks just like 1 minus cosine of x all being squared, right? Like if you let u equal cosine of x, we're not going to actually write it out that way, but if we did, we'd have 1 minus 2u plus u squared, which we should know is 1 minus u squared. So in other words, it's just 1 minus cosine x squared for that piece of it. So if I break that down as its own limit, 1 minus cosine x squared over x squared, all that's left is minus, because we have a minus sign in front of that 3x squared, a limit as x approaches 0 of 3x squared over x squared. Since both my numerator and my denominator are being squared in that first limit, I can pull that outside the entire limit. And we would see that that limit inside of there is the limit that we proved in class to be 0. So that'll become 0 in just a second. And then this other one, well, 3x squared over x squared is just 3, right? So we have minus the limit as x approaches 0 of just 3. We know that the limit as x approaches 0 of 1 minus cosine x over x is 0. So this is now just 0 squared minus, well, the limit of a constant is the constant. So 0 squared minus 3 is negative 3. For our next one here, we'll see that our sine is being cubed and our u is being cubed. So what we'll want to do is we'll want to take that cubed outside of everything, but I can't do that because the 32 is not being cubed. Now you can do some kind of creative arithmetic to help yourself to only pull part of that constant out and deal with it with that 4u, right? Because I need to have a 4 being cubed in the denominator also, but I think it's usually just easier to just pull the full constant out and then deal with the simplification later. So I'm going to rewrite this as 1/32, the limit as u approaches 0, of now sine of 4u over, that's an x, plus sine of 4u, probably write the right variable, sine of 4u over u, all being cubed. And what we want inside is a 4u in the denominator. So I'll put that 4 in the denominator and a 4 in the numerator. I'll pull the 4 in the numerator out, remembering that it's being cubed. So we'll end up with 4 cubed, which is 64 over 32, times a limit as u approaches 0, that I'm now pulling that cubed outside the whole limit, right? Sine 4u over 4u, all being raised to the power of 3. Well, 64 over 32 is just 2, so we have 2 times that limit is 1, so 1 cubed, or just 2. All right, for this next one, we're looking at the limit as x approaches infinity of 3x cubed minus 6x plus 1 over 6x squared plus 2x minus 7, which is, of course, infinity over infinity. So the way that we've worked on to deal with this in class was we've just divided everything by the highest power that we have. So our highest power is x cubed in the entire problem. So we're just going to divide everything in here by x cubed. So 3x cubed over x cubed minus 6x over x cubed plus 1 over x cubed, all divided by 6x squared over x cubed and plus 2x over x cubed minus 7 over x cubed. So there's a little bit of simplification that we can do there. And of course, we can, just like we can multiply the top and the bottom of a fraction by something, we can divide the top and bottom of a fraction by something. So no breaking of math rules there. This becomes a limit as x approaches infinity of now a 3 minus 6 over x squared plus 1 over x cubed in our numerator. And in the denominator, a 6 over x plus a 2 over x squared minus a 7 over x cubed. And as x goes to infinity, well, 6 over infinity squared is 0, right? 6 over a really big number is approaching 0. And 1 over a really big number is approaching 0. And 6 over a big number is approaching 0. And 2 over a big number is approaching 0. And all of these that are over an x squared are all approaching, or over an x cubed, or just over an x. They're all approaching 0. So we end up with 3 over 0, which is undefined, which tells us that the limit does not exist. It's a similar problem here. We have limit as x approaches negative infinity of 2x plus 7 over 7x minus 1. If I were to plug in negative infinity to both the numerator and the denominator, they'd both be negative infinity, right? Which is negative infinity over negative infinity, which is indeterminate. So we can use that same trick. We'll just divide everything by the highest power. The highest power is just x to the first power. So we'll do 2x over x plus 7 over x over 7x over x minus 1 over x, which just becomes a limit as x approaches negative infinity of 2 plus 7 over x all over 7 minus 1 over x. The 7 over x and the 1 over x go towards 0, and we just get a limit as x approaches negative infinity of 2/7. Oops. And you really don't even need the limit anymore, and we just get 2/7. This one is a similar problem. Right, again, it's infinity over infinity. So we're just going to use that same trick. This time our highest power is x to the 4th. So we're going to divide everything by x to the 4th. And as we do that, term by term, right, x cubed over x to the 4th is 1 over x. And then minus 1 over x cubed plus 5 over x to the 4th. All over 1 plus 1 over x squared plus 2 over x cubed. And everything in the numerator this time goes towards 0, as do most of the things in the denominator. And we're just left with 0 over 1, which is, of course, 0. So for this next one, we got to be a little bit careful, right? Because we've got a limit as x approaches negative infinity of 5x minus 7 over root 4x squared plus 5. So the numerator is negative infinity, right? In the denominator, well, if we square negative infinity, that's positive infinity, and multiply it by 4 and add 5 is still positive infinity, and square rooted is still positive infinity, right? So we get a negative infinity over a positive infinity, which is indeterminate. So what we have to do here is we have to still use that same idea where we want to divide by the highest power, but the highest power is kind of a little tricky here. It's not exactly x squared. It's definitely not x squared because the x squared is being square rooted, but it's not quite x, right? But it's sort of x because the square root of x squared is like x, and we've got an x in the numerator. So we're going to try and divide everything by, we're just going to divide it by the square root of x squared. And so when I do that, it's in the denominator, I'm going to have a square root of 4x squared plus 5, all divided by x squared inside the square root. So that's dividing by the square root of x squared. But I'll do the same in the numerator, right? 5x minus 7 over the square root of x squared. But I can't really do that. And I can't also say that the square root of x squared is just equal to x, because that's not always true. As we've talked about in class, the square root of x squared is the same thing as the absolute value of x. Because if you take a positive number and square it, and then square root it, you get the positive number back, or if you do that with 0. If you take a negative number, though, and square it, and then square root it, you get the positive version of it, which is exactly what absolute value does. And then we need to remember that absolute value of x equals x if x is greater than or equal to 0, and absolute value of x equals the opposite of x if x is less than 0. So in this case, the square root of x squared is equal to the absolute value of x. But for our purposes, x is approaching negative infinity, which means that x is less than 0, which means that the absolute value of x is equal to the opposite of x. So what we want to do is we actually want to divide that numerator by the opposite of x. Right? 5x minus 7 over the opposite of x. And then in the denominator, we just have the square root of 4 plus 5 over x squared if we simplify that out. As we continue on, we should get a limit as x approaches negative infinity. And now when we divide 5x by negative x, we get negative 5. And negative 7 by negative x, we get plus 7 over x. Our denominator still looks the same. And as x goes to negative infinity, 7 over x is like 0, and 5 over x squared is like 0. So this just becomes negative 5 over the square root of 4, which is negative 5 over 2. So be extra careful with these ones that involve square roots of x squared. I like to put those on the test, so I would definitely keep an eye on those. And remember that if x was approaching positive infinity, right, then our x would be greater than or equal to 0, so the absolute value of x would become x instead of the opposite of x. All right, for this one, we have the limit as x approaches infinity of 2e to the 2x plus 3e. This is actually probably the easiest question on the test, or not on the test, but on this assignment. This would be 2e to the infinity just plus some constant. Well, e to the infinity is infinity, and if we add more to it, we just get infinity. And remember that infinite limits technically don't exist. Right? So this limit technically doesn't exist, but it's going towards infinity, so we can write that. For this next one, it looks like it's a pretty complicated problem here, and it kind of is. We can plug in negative infinity, and we see that we get e to the negative infinity here. Well, e to the negative infinity is 0, right? So that's fine. But then we get minus 0 again, and then plus 0. But then we get minus e to the negative infinity, which would be negative e to the negative infinity, and e to the negative infinity, would be e to the positive infinity. E to the positive infinity is just infinity. And the same thing happens down here. We get e to the negative infinity, which is e to the positive infinity, which is infinity. So we have a bunch of zeros, and then minus infinity plus infinity. And minus infinity plus infinity is the same thing as infinity minus infinity, which we talked about in class. That's one of our indeterminate forms. So we have to do a little bit of algebraic work here to deal with this. Now, we don't have to do any algebraic work with these first three terms if we don't want to, right? Because the limit as x approaches negative infinity of e to the 10x minus 9e to the 3x plus e to the 2x, that's all just 0, right? And then we've got, we'll say plus the limit as x approaches negative infinity of negative 3e to the negative 2x plus 3e to the negative 11x. So the two that are problematic will separate out into their own limit. And then the ones that aren't, we'll just call them all 0. So this is now just 0 plus this other limit. Well, for this other limit, what we want to do is we want to try and turn, I don't know why I have a negative there, let's fix that. We want to try and turn these negative exponents into positive exponents. So what we'll do is we'll just factor out e to the negative 11x out of these two terms. So I'm going to have a limit as x approaches negative infinity of e to the negative 11x times whatever I get when I factor that out. Well, the negative 3 will still be there, and then it's going to be e to some power. And we have to remember how exponent rules work, that the thing outside of here, when I distribute it through, right, when I multiply that by this e to whatever power, I need to get negative 3e to the negative 2x. And exponent rules say add those exponents when you multiply. So negative 11x plus 9x should be e to the negative 2x, right? And so then we also end up here with just a plus 3, right, if I factored out e to the negative 11x. So now this is equal to, well, e to the negative 11 times negative infinity is just e to the infinity, or infinity, times negative 3 times e to the negative infinity is just 0 plus 3. And, well, 3 times infinity is just infinity. For this next one, we've got, if we plug this in, we get infinity plus infinity. And then the minus 3e to the negative infinity is just a minus 0, and then plus a 0, because those both are e to the negative infinity, which are 0. Well, infinity plus infinity is not indeterminate. It's just infinity. So that one's pretty straightforward. Now, if this had happened to be a minus sign, then we'd have to do a similar thing to what we did in the previous problem, where we factored out an e to the positive 3x. And we could leave these two off by themselves, and then we'd factor an e to the 3x out of these two. And that would allow us to solve this problem. All right, for this next one, we're just going to do a little basic u substitution. We'll say let u equal 2x to the 4th minus x plus 5. And as x approaches negative infinity, we have to figure out what u is approaching. Well, we should know from our discussions in class that the 2x to the 4th power dominates the minus x and the plus 5. But even if we weren't sure of that, right, we could rewrite the u. We could factor the x to the fourth out and leave it as x to the fourth times 2 minus x to the negative 3, which x to the negative 3 is just the same as 1 over x cubed. And then plus 5 over x to the fourth. Right? And then we can see that as x goes to negative infinity, this is like 0 and this is like 0. And so we just end up with u is really just like x to the fourth times 2, right? Well, if x is negative infinity, then that would be negative infinity to the fourth, which is positive infinity. So you don't have to show all of this work out, but that's why we can say that the 2x to the fourth dominates. And this just becomes a limit as u approaches positive infinity now of the natural log of u. And of course, what do we know about the natural log function? Well, it looks like this, and as x goes to infinity, it increases without bound. Very slowly, but it does increase without bound towards infinity forever. All right, and here's our last one. And for this one, we're going to use the same idea here. We're going to let u equal 7 over x to the 6th minus 5x. And as x goes to negative infinity, we want to see what u is approaching. Well, u is approaching 7 over something, right? And in the denominator, the 6th power is going to dominate the negative 5x. So we'll look at negative infinity to the positive 6th power should come out to be a positive infinity. So we might be tempted to just say this is equal to 0. And so I'm going to write that out, but this is not what we want to do, right? So limit as u approaches 0 of the natural log of u. Well, we just looked at the graph of the natural log, right? It looks like this. We can't have a limit as u approaches 0, right? Because I don't have stuff to the left and to the right of 0. So we have to just be a little bit more careful and note that 7 is positive and infinity is positive. And if I take a positive number and divide it by a positive number, it will always be a positive number, which means if I'm approaching 0, but I'm always a positive number, I would be approaching 0 from the right-hand side. So this is actually a limit as u approaches 0 from the right-hand side of natural log of u, which we can do here. We can see it goes down at that vertical asymptote to negative infinity. So be extra careful with these ones. With the natural log where the u looks like it's approaching 0. You need to decide if it's approaching 0 from the right or 0 from the left, because it significantly changes the answer to the question. So that's our last problem in the walkthrough for the limits for homework assignment. And I got lots more limits to talk about and learn in this unit, but that's it for this time.